Okay, good morning, everyone. I want to believe those of you at the back, you can hear me clearly, right? I want to welcome you to another week. And of course, um, this is statistical machine learning class. Let me prepare your mind. We're actually going tough, but you know what? If you pay attention and you ask question when you get stuck, you should be fine. I want to welcome you to another algorithm for clustering. All this while we'll be focusing on hard clustering. When I say hard clustering, I actually means a situation where we are deterministic when we are assigning object to groups. Deterministic in the sense that the moment you have objects in one group, that object cannot be in another group. But we realize that in some situations, there's possibility of overlapping, where instead of us to use deterministic assignment, we're actually going to go probabilistic. Or probabilistic in the sense that objects can actually belong to more than one group. Or what we just need to do, what is the probability that is going to be in this group, the probability that is going to be in that group. Now, to be able to do that, we need soft algorithm. And of course, one of the soft algorithm is what we call the Gaussian mixture model. I want to welcome you to Gaussian mixture model. It's an algorithm, it's classified under soft uh, clustering. Okay, now in the outline, I'm going to walk you through the concept of Gaussian mixture model. And I'm going to use Minnesota crime data to explain Gaussian mixture model. And I'm also going to justify the reason why any of the hard clustering algorithm that we've done before, the K-mean, the K-midoid, hierarchical, clustering may not be appropriate in a situation where where we have overlapping. Okay, I'm going to explain that to you. And of course, the method that we use, the approach in the Gaussian mixture model, we use what we call expectation maximization. Okay, I'm going to walk you through how that is going to work. Then how do we do it now? I'm also going to walk you through that. Well, you know what I'm begging you for? Please pay attention. If you get stuck, if you need clarification, make sure you ask. Now take a look at this. Okay. If I have a situation looking like this, I want to believe you've seen stuff like this before. This is looking like a mixture of a normal distribution. We could have situation whereby maybe crime activity could overlap between cities. Okay. If you take a look at this, using a K-middle or K-mean here, it's not going to work. Using a K-midoid is not going to work. The K-mean, the K-midoid, all of that, uh, they actually use deterministic assignment. There's nothing probabilistic because the assignment is hard. Okay. If I'm going to give you the example in Minnesota, okay, I want to talk about Minnesota crime data. Okay. Based on maybe 2024, like I have a 10,000 incident of crime in Minnesota. And of course, uh, if we use like three clusters, there's possibility of crime overlap between cities. Okay, crime can overlap between downtown Minneapolis and around University of Minnesota. Okay, situation where there's overlapping, okay, the clustering is not going to do a great job. And that's why we need a mixture of Gaussian distribution that will allow some kind of overlapping. And let me also tell you this. the benefit is that this is going to bring. We're also going to have a way to measure the shape. Okay, the shape of a cluster, not only the centroid. With the k-means, we're not able to measure the spread. Okay, we don't put into consideration the variance of a cluster or the covariance of a cluster. We don't put into the only thing we care to know about in the k-means is sera, which is the centroid. Okay, if you take a look at what I'm trying to show you now, we have a mixture of two normal distribution, even though they got the same center, but they have different spread. Can you see the way which one is more spread out of the blue and red? Can someone tell me? Okay, the blue is more spread out, which means that has more variance compared to that. That is the same way we're going to look into some crime incidents. When you classify them into a cluster, we look at the variance within the cluster. Take a look at this. The k-means only help with spherical shapes like this. Situation where you have a non-spherical or you have a elliptical shape, it's not going to do that. Like this. Take a look at this. Can you see this? There's a kind of overlapping. If you take a look at this, give me 1 second. If you take a look at this, can you see overlapping here? Okay, this is a situation whereby maybe the crime incident overlap between two cities, okay, that are very close. If you want to put into consideration the crime data in Minnesota, you want to talk about the downtown Minneapolis and the around University of Minnesota, they do overlap. Okay, K means it's not going to perform a great job here. We need a Gaussian mixture of model. Okay, and the advantage of the Gaussian mixture model is like it can handle elliptical shapes. Okay, K-means cannot handle elliptical shapes. Okay, now, and of course, this allows the probabilistic assignment, because the probabilistic assignment, because in the sense that we can have some here, they can also belong here. When I partition uh, Minnesota into 3 clusters, believing that each cluster is from a Gaussian distribution, instead of me to say that robberies or burglary only take place in North Minneapolis, I'm not going to say that. I'm going to give the probability of robbery in North Minneapolis. I'm also going to give the probability in around University of Minnesota. I'm also going to give the probability in the downtown Minneapolis or North Minneapolis. Okay, so that is what we mean here. You know what? We want a situation whereby we don't want to waste community resources and police don't just go out. Okay, this is a data-driven policing. Okay, we want a situation whereby they are going out to be guided statistically, and that will enable them to manage resources. Okay, take a look at this. Okay, this is obvious Gaussian. This is overlapping. If you take a look at the shape. Now, if I'm assuming 3 clusters right now, where they can be overlapping, take a look at this. Okay, I'm actually going to use Gaussian. This is a Gaussian mixture of distribution. I have 3 clusters. Okay, and each of them, we have their means, and each of them, we have their variances. Situation where I have one variable, okay, I'm going to be talking about variance. If I have more than one variable, I'm going to be talking about covariances. Now, if I want to put into consideration, talking about the Minnesota crime data, of course, what am I trying to say? The variables is not just going to be one. Okay, where crime is committed, okay, number one variable is what is the type of crime? Is it burglary? Is it property theft? And something like that, type of crime. It's one of the variable. Number 2, I need to look into the latitude and the longitude for me to detect geographical location. Okay. Number 3, I want to be able to see whether that very crime occurred during the day or during the night. I also want to see whether it occur during the weekend or during the weekday. So what I'm trying to talk about, there's so many variables involved. And since there's going to be so many variables involved, then each cluster will have a vector mean, and they're going to have covariances. Does that make sense? Okay, so this is uh, a typical picture of a Gaussian, mutual of Gaussian normal distribution. Okay, the mutual of Gaussian distribution. So we believe that each cluster is derived according to the Gaussian distribution, and they're going to have their parameters. Okay, each cluster they're going to have three parameters. The first one is the mean. The second one is the covariance, and the third one is the probability of, objects being classified into that particular cluster. So there are three parameters involved. Now, because of that, I'm actually going to show you a formula for Gaussian normal, the Gaussian distribution. We have there are different kind of Gaussian distribution. If I'm focusing on one variable at a time, I'm going to have a univariate normal. If I'm focusing on two variables, I'm going to have a bivariate normal. If I'm focusing on more than two variables, I'm actually going to have multivariate. In this case, because the variables are likely going to be more than two, I will be focusing on multivariate. Take a look at this. This is multivariate normal. Has anybody seen this before? Okay, this is multivariate normal. Why are we using multivariate normal? We're using multivariate normal because so many variables are involved, not just one variable, and they are distributed according to normal distribution. Okay, now I was saying something the other time. Let me tell you this. I wanted to see that these shapes, they have different cluster. I mean, they have different center, right? The center here is different from center here, is different from center here. And of course, uh, there is overlapping, okay, between them. And not only that, in the case of Minnesota, okay, where hotspots of crime can overlap between cities, I'm actually going to have elliptical shape. Okay, what determines the shape here is actually the covariance structure. Covariance determine the shape. Okay, at times, if I have three clusters that I mentioned the other time, I mentioned downtown Minneapolis, I mentioned North Minneapolis, I mentioned around University of Minnesota, there's going to be ellipse on each of that. One is going to have red ellipse. Maybe the one with the red ellipse may actually be the one where you have a violent crime. There's going to be blue ellipse and there's going to be green ellipse. Okay, there will be green ellipse around University of Minnesota because they normally have incidents of property theft. Okay, so take a look at that. That's what I mean. Okay, now I need you to pay attention. If you don't understand, ask me a question. Imagine if I have 1,000 set of data, or maybe I have 1,000 incident of crime. 1,000 incident of crime, and I only have three variables. That's why you see 1,000 by 3. Can you see that? 1,000 by 3. The observation is 1,000. The observation you want to classify is 1,000. Okay, it could be a crime incident. Okay, or it could be series. Okay, but three variables here is actually that's why you see 1,000 by 3. And of course, if you have a situation where in a cluster there's going to be a mean vector, okay, and that will be 1 by 3, okay. And let me tell you this: the covariance. This shape is a covariance. It's going to be a square matrix. It's going to be 3 by 3. If I have three features, okay, the covariance will be 3 by 3 in this cluster. If I have 4 features, it's going to be 4 by 4. If I have 5 features, it's going to be 5 by 5. Does that make sense? Okay. Now, let me also say this. Okay, if one of the variable is type of crime, okay, then I'm going to say, oh, if the type of crime, if I'm focusing on robbery, I'm going to say, oh, 70% in North Minneapolis, or 20% in downtown Minneapolis, and maybe 10% around University of Minnesota. That is probabilistic assignment. I'm not going to say a particular crime is only restricted to a particular cluster. We're not going to say that. We're going to allow overlapping here. Okay, please pay attention. Today, there's going to be a lot of theoretical stuff. But you know what? I understand my mathematics, I understand my statistics, and I understand machine learning very, very well because I'm able to relate notation, symbols to real life. Now, I said something the other time. We're going to have three parameters involved. We're going to have a mean, we're going to have covariance, and we're going to have a missing probability. Now, what we want to do right now, I want us to set up. I want to set up the formula now. What am I showing you on the board right now? Okay. I want to believe every crime incident, okay, is actually going to be represented as a Z1, Z2, up to ZK. Why am I stopping at ZK? Because I want to consider K number of clusters. Now, the Z1 is going to be 1 before I can classify that into this particular cluster. Okay, and that's why if you take a look, before I can classify something into a particular cluster, what I'm trying to say here, the probability of Z1 equal to 1, Z2 equal to 2, ZK equal to that, and I'm going to raise that to power Z1. And if you take a look at all of this, if I want to write this in a short form, what am I doing here? That is like multiplying, right? What is the shortest way to write? Because all these are going to be independent. Okay, then I can do this. That pi that you see is talking about products. It's more like, and the probability of each one, the probability of a zi, okay, the probability is actually the pi that we're talking about. For instance, what is the probability of z1? It's going to be pi 1. Pi 1 is the missing probability, the probability of belonging to a particular cluster. Don't forget here, we actually using a probabilistic assignment against deterministic assignment. Okay, the probability of Z now have been derived to be equal to this. The next in the derivation now, please pay attention. The next in the derivation now is, I want to be able to tell the world, this is trying to say, okay, we're dealing with a normal distribution. It's going to be a product of a normal distribution. Okay, if you see that very end, okay, we have the the variable Sn follow normal distribution, okay, and we have for k number of clusters, each cluster has its own vector mean and variance covariance. That is what this guy is talking about. Okay, so here now, okay, if you take a look at this guy, this is just a probability of Z. Okay, but if you take a look at this, okay, here I choose an observation, xn, an observation that I want to, okay, I choose an observation xn, okay, and what is the probability of a z given that observation xn? That's what I want to find now, which is going to be the product, okay, a product of normal distributions, okay, and of course, what are we doing here? This is more or less like I'm multiplying the distribution, the normal distribution for cluster 1, the distribution for cluster 2, until I get to distribution for cluster K. That's exactly what I'm doing here. Now, I need you to pay attention to something. This is conditional because the way we're going to set up the probability, we want to be able to update on the parameter. And because of that, we're actually going to use the idea of Reverend Thomas Bayes 1759 to do that. We're gonna go Bayesian. Has anybody heard about Bayesian statistics before? Okay, we're gonna go Bayesian. We're gonna create a posterior probability. Okay, so right now this is conditional probability, the probability of Xn given Z. And don't forget, we already have the probability of a Z. Okay, we have a probability of a Z because let me tell you this. We normally have a prior probability. The prior probability, the prior probability is the probability of a state of nature before having evidence. Okay, what is the probability before doing anything at all? What is the probability that this particular crime belongs to this particular community? Stuff like that. Okay, so if I have that, now this is this is like a likelihood now. Okay, the probability of Sn given Z. Okay, then the next thing I'm going to do is, can I find the probability of a joint? Where Xn and oh my God, do you remember what you've done before? Okay, under probability, the probability of A intersection B, okay, if A and B are independent, it's going to be equal to the probability of A, okay? So let's say they are not independent, okay? Not independent, I'm only going to have this, the probability of B given A. Okay, you've done this before. Okay, if A and B are not independent, okay, the probability of A intersection B will be probability of A multiplied by probability of B given A. But if they are independent, it's just going to be product of probability of A and B and probability of B. So what do you think I'm doing right now? I want to find the probability of the joint occurrence of S and N observation, and the latent variable Z, of course, is going to be this guy. And you know what? We've seen the probability of Z here. Can you see that? The probability of Z, we've derived it to be this guy. And we've also seen the probability of Xn given Z. Then I can now find the probability, okay? I can find the probability, so I can find the probability of this. Or what I'm just going to do is to multiply this expression for this by that, okay? And when I do that, okay, I'm actually going to be using, I'm going to use this to multiply this, okay? But you know what? Another thing that is of interest, can I also have a way, take a look at this from here. If I'm only focusing, if I want to focus on a particular observation that we call marginal probability in probability theory, okay, what am I going to do? What I'm actually going to do, since this is the probability of the joint, this guy represents the probability of the joint of two variables, Xn and Z. Can I find marginal? This guy is going to be marginal, okay? The marginal probability is when I'm only interested in one variable at a time. If I'm interested in one variable at a time, that is going to be this guy. It's going to be sum, okay, that very joint, okay, from K star from 1 to n. And you know what? What I'm going to do now, please pay attention. This guy is this guy. Okay, this guy is the normal distribution. If you want to come back here, okay, this is the normal, and that guy is that guy. If I plug them in, I'm having this. Is there anyone in this class who doesn't understand this? What do I have now? Go ahead. You mean why are they not in the which one? Okay, this is what happened. Let's say right now, I want to do this. The probability of xn is the same thing as that. Have you heard about total probability before? Total probability. Now, what I'm just going to be doing is I'm going to plug in what is the probability of z? The probability of z is actually going to be pi k. I'm going to take you back. Do you see that? The probability of z, like if I'm interested in just a single z, it's going to be pi k, right? Then what about the probability of xn given z? Do you see? Sn. I'm only talking about one cluster this time around, not all the cluster. This one is talking about all the cluster, but I'm interested in a particular cluster. Does that make sense? Now from there, I plug in that one. This is what I have now. But you know what? If you take a look at this, if you take a look at this, I'm only focusing on just one cluster. But if I now pull this, then I'm looking into the totality of all the clusters. Go ahead. Oh, the power of zk. Yeah, is it going to come in? You know, even pi k also. Okay, that's a good question. I'm going to take you back. Do you see that pi k also has that power? We see come into that. That's a good question. Okay, the two of them has that power. We see come into that. Now, based on what we have now, okay, based on this, okay, based on what we have now, okay, now take a look at this. Now, if you take a look, I want to focus on the probability of x. And you know, when you take a look, when you talk about x, I told you the other time, we actually gonna have not just a single x, okay? And because x1, x2 up to xn, they're gonna be independent. When x1, x2 up to xn are independent, what do? We do the product, right? That is what this guy is trying to say. That first one is saying when x1, x2 up to xn are independent, then I'm just going to do the product of the marginals. Now, please pay attention. Do you know that this one is just this guy here? Just for the probability of a particular x. Does that make sense? But if I have so many, if I have x1, f2 up to whatever, then I'm actually going to have this. Then this is what is going to, do you know what that guy is doing? It's saying that I'm multiplying this guy n times. Does that make sense? That is, so this guy at the back here means I want to consider probability of x1, probability of x2, probability of x3. Then what is the probability of the joint occurrences of x1 up to xn? That is going to be the product of the respective probability. That's exactly what we have. Now, the next that we're going to do is take a look at this. We take the log of that, natural log. Okay. Now, when we take the natural log, we're going to have this. Why? Why are we having that? Please pay attention. Why are we having that? Okay. If I have pi 1, if I have pi 1 and x mu 1, this one, if you take a look at this one, okay. Now, uh, if I have a lane, you know, if I'm taking the lane of both sides, okay, the lane of a product is just like lane of A, B, C in maths is lane A plus lane B plus lane C, right? Now, this guy here, actually means a product. If I take the ln of a product, then it's going to be summation of the ln. Ln of a product, natural log of a product ABC is going to be the log of A plus log of B plus, and that was why you have a summation at the beginning. Is there anyone in this class who doesn't understand how that summation appears? Anyone who doesn't understand how that summation appears? How this summation here? 1 second. How this guy appear? It appear because I'm taking the log of a product. Okay, this guy is a product. The log of a product will be the sum of the log. We use our mathematical knowledge in machine learning world and in statistics in general. Now that gives us equation 3. Now after that, okay, because we actually want to build posterior, okay, take a look at this. I told you the other time, probability of a zk equal to 1 with pi k, that's a missing one. And this is a probability distribution for a particular cluster. This is to tell the world that, okay, for cluster K, of course, in cluster K, in a particular cluster, we have all the type of variables. We have the variables, all the features. All features in cluster 1, all features in cluster 2, all features in cluster 3. Does that make sense? Up to cluster K. Now, you know where we're going now. If you take a look at this, this is a posterior. What is the probability of a zk equal to 1 given Sn? Look at the likelihood. Sn given z is the likelihood. If you take a look at what I've done, look at that. There's a difference between xn given z. That's a likelihood. If I now consider the probability of z now given Sn, that's a posterior. Now, because we're using the knowledge of Bayes' theorem, okay, equation 4 become posterior. The denominator in equation 4 is the sum of the numerator. Do you see that? In the Bayes theorem, okay, in Bayes theorem, if you have the probability of AI given B is the same as probability of B given AI multiplied by probability of AI divided by summation, the probability of B given AI, the probability of I start from 1 to K. This is a Bayes theorem. We're using the idea of a Bayes theorem. Okay, if you look at equation 4 now, that is posterior. Okay, the posterior density, because the way we're going to assign probability, we're going to assign object. We assign object to group the object with the highest posterior, and that is why this is like how do we actually arrive at the posterior density is what I've been showing you. Okay, but let me tell you this. If you take a look at this posterior density, equation 4, what are the parameters? Okay, the mean, the covariance, and the missing probability. Those are the 3 parameters. Now, what do we want to optimize? We want to optimize. Those are the 3 parameters. Can you see that? Pi. Pi is the probability of a crime incident being classified into a cluster. Okay, mu is the mean. Okay, like a center for that particular cluster. And of course, the other guy is a covariance matrix that will tell us the shape of each cluster. And let's take a look at the step. Okay, the step here is what we call expectation maximization algorithm. Okay, let me tell you this. We're going to start by initialization. Okay, we initialize our parameter. Initializing parameter is like we're going to start with some values for mu, values for pi, maybe based on historical data. Okay, we're going to start with that. Okay, and that is what we call here a very good way to have initial values for mu, for missing parameter. If you don't want to go by historical data, we can use a k-means. K-means will help us in estimating what is the mu, what is the covariance, what is the missing parameter, and that is for the initial values that we're going to start with, because We don't choose initial values arbitrarily. Otherwise, the Gaussian mixture model is not going to work well. And that's why we can use k-means, okay, to estimate those parameters. Then from there, that is all the expectation step, as you can see. Now, the next is if you take a look now, based on the question that you asked the other time, okay, in the optimization, we're now going to raise the pi. Can you see now? We're raising that to power znk, and that one to power znk when we want to when we want to do the optimization. Okay, and right now, take a look at that. The next, we take the ln. Why are we taking the ln of this? Because this is in optimization, this is multiplicative, and that would be difficult to optimize. Then we take the logarithm. You know, in mathematics, when you take the logarithm, the power is going to come down, right? And this is going to become additive. Additive will be very easy to optimize. Okay, now taking the log of that, we're having this guy now. Can you see now? It's easy now. Why? You can see additive now because when you have a log, okay, when you take the log of a multiplicative, this is multiplicative. I'm taking the log of this guy, the log of that. It's going to be log of this plus log of that. And that was why you have this guy here. You have equation 7. Okay, you can see. So, and this guy that was up before, this guy that happens to be the power, when you take the log, it's going to come down, right? Okay, you remember in your maths, if you have log a b, a raised to power b, that what is going to happen? This is going to be b log a, right? Okay, so you can see that guy coming down. Okay, now the guy come down now. Can you see it? Can you see it here? It come down after introducing the log. Now we have equation 7. Now, equation 7 is what we want to optimize. What are we optimizing this equation 7 for? We're optimizing this equation 7 because we want to figure out the optimal values of pi, okay, for each category, for each cluster. We want to get the mean for each cluster. We want to get the optimal covariance for each cluster. But don't forget, it's an algorithm. We need to have initial values for them before we do that. And I said the initial values can be obtained using the k-means. Okay, now another thing we're going to do now, so this guy now is this. Okay, this is just to say that this guy here is the same as this guy, okay, based on what we've done before. Now the next thing we're going to do, we have equation 8 that we want to optimize, but we need to place a restriction. We actually, we're optimizing, we are finding the maximum because we're using the method of maximum likelihood to estimate the parameters. So we want to figure out what is the values of theta that will give us the maximum of those functions. And because of that, the way it is now, the algorithm may get into a problem. We need to impose a restriction. And this is the restriction that we're going to impose. Pay attention. We're imposing this. Has anybody seen stuff like that? There's something that we call Lagrange multiplier. Okay, this is we are trying to say the sum. What is the sum of pi k? What is the sum of probability? 1, right? And 1 minus 1 is 0, right? So this is a constraint optimization. In a constraint optimization, initially this is what we have. Then we're going to impose Lagrange. That's what we call Lagrange multiplier. If you don't, because you have to, if you don't impose that condition, there is possibility your missing probability will go outside 0, 1. We don't want probability to go outside 0, 1, and that's why you are imposing a constraint. And this kind of constraint is called Lagrange multiplier. Does that make sense? We're imposing the condition that the sum of a pi must be 1. Does that make sense? Now we're going to use differentiation. We're going to differentiate with respect to pi k, okay, and set to 0. We're going to do that, and when we set to 0, this is going to be the optimal pi k. okay, which is going to be like the optimal pi k is going to be, that pi k means the probability of object belonging to cluster 1, belonging to cluster 2, and so on like that. You can figure that out. And not only that, you're also going to update. This is going to be the optima, okay? The optimal value for the mean, the optimal value for the covariance. You are never going to have an optimal value for this if you don't start with initial values. And I told you the use of k-means algorithm can be used to figure out the initial values. Of course, if you want to go into iterative procedure, you need to start with the good initial value. But what I'm trying to say, at the end of the day, you're going to have this. These are optimal. Now, I'm going to use my last step. Go ahead. Okay, I'm going to circle that. Are you talking about the one here? Which one? Oh, this one. Oh, okay. The gamma, I'm gonna show you something now. That's a good question. This guy, I'll quickly gonna take you backwards so that you're gonna see what I'm talking about. 1 second. Oh, it's right here. Can you see this guy? The posterior probability. Can you see that? Yeah. So that's like a posterior probability. Now that you understand that, we've gotten all of that, that the next thing I'm actually gonna do now, all what I've been walking you through is just what happened behind the scene and how we're able to arrive at the three parameters. Initially, we started using initial values for the three parameter, and I said we don't choose that arbitrarily. We use k-means to determine that. Then we now start using that in our algorithm, and eventually they're going to converge. So what we're trying to say, the formula behind the scene for the mean is this guy, mean of each cluster, the optimal one, the one that has been updated, and the covariance formula is that. And the one for the missing parameter, the probability to allocate is this. We got this through optimization process. But you know what I want to walk you through now? How do we do this in R? Please pay attention. Now, and do this in R, you're going to load a package called this M cross. Now, you know what I want to do? I want to deliberately simulate data, and I want to have data for three clusters. Please pay attention. I'm simulating from Gaussian. This is how to simulate from normal. Okay, for each category, I'm simulating 100 data set with a mean of zero standard deviation 1. And how many column? Number of column equal to 2 means I'm focusing on two variables. Does that make sense? Okay, now I simulated that. Now I want to use the GMM now. Okay, you see the MC clause. Don't forget, I need to load this package. Do you see that package? Okay, now I actually gonna have this guy. Now let's see what is gonna come out. Okay, we want to do the classification, we want to make prediction now. Okay, can you see that? 1 1 1 1 1 1 2 2 2 2 2 2 3 3 3 3 means observation that will be in group 1, the other one in group 2, and so on like that. Okay, let us have a visual. Let's visualize the result. Can you see the result? You can see some overlap in here, right? Look at these two. I was talking about the other time, I was talking about downtown Minneapolis and around University of Minnesota, there's possibility crime event overlap. Take a look at that. Okay. Now, now, uh, synthetic data with normal. Now, I want to situate. You know what I want to do now? I want to simulate, data